Thank you. So as Daniel mentioned, I'm Oren from Carnegie Mellon University. I'm at the Robotics Institute. And I'm going to talk about motion planning. So informally, before I go into the talk, what's motion planning? We have a robot. In this case, this is Herb, the flagship robot of the Personal Robotics Lab. And we need to move from one position to another while avoiding contact with obstacles. And the general motion planning problem, the way I presented it, is computationally hard. So exact solutions are intractable. And the way we usually study these types of problems is in what's called a configuration space. A configuration is some d-dimensional point that describes the position orientation of the robot. And the configuration space is a space of all configurations. It's a d-dimensional, typically high-dimensional space. Some of it have obstacles, which correspond to placement of the robot that intersect obstacles in the environment, or self-collisions. So the configuration space is subdivided into the free space and the forbidden space. And as I mentioned, the general problem is computational hard with respect to the number of degrees of freedom, the dimension of the configuration space. So the common approach in robotics for probably the past 20 years is what's called roadmap-based methods. In these methods, we abstract or approximate the structure of the continuous configuration space using a discrete graph, which we're going to call a roadmap. Vertices of this graph correspond to configurations. Edges correspond to local motions connecting close-by configurations. And if all the vertices and edges are collision-free, then basically we can run any shortest path algorithm, Dijkstra A*, or your favorite shortest path algorithm on this roadmap. So let's kind of visualize how this looks. The way that we generate these roadmaps, we throw a bunch of samples in the configuration space. Some of them correspond to configurations that lie in the obstacle space. So we need to run some collision detector which checks if these configurations are collision-free or not. We'll throw them away. Then we're going to connect every two close-by configuration using some local planner and some nearest neighbor data structure. Again, some of these configurations, some of these edges intersect obstacle. This corresponds to motions of the robot where he intersects an obstacle or itself. Using the same collision detector, we're going to throw these guys away. And now we have a graph which is completely collision-free. And we can run our search algorithm. So this meta approach, or this family of algorithm, has been floating around in the robotics community for 20 years. And this is the path planning. What I'm going to concentrate on this talk is two aspects, the collision detector and the path planner in this meta approach. And to understand the domain-specific challenges in robotics using this approach is that evaluating if an edge is collision-free or not is the computational bottleneck of all these algorithms. So it's not node expansions as usually is considered in A* type algorithms, but what we call edge evaluation, testing if an edge is collision-free or not. And in some cases, it's been reported that 99% of the planning time was devoted to edge evaluations, not to the actual search, but just to checking if the robot intersects obstacles or not. And a common way to treat this computational bottleneck is using what's called lazy edge evaluation. And the idea is to delay testing if an edge is collision-free or not until absolutely necessary. One of these algorithms, LAZYSP, was presented here in ICAPS 2 years ago. It's a family of lazy algorithms. And the authors, Christel and Srinivasa, empirically showed that this algorithm works really well on a wide variety of real-world robotic applications. So the question we came to ask in this work is, can we give some theoretic analysis that matches, that explains why these empirical results are so well? So what we set to do is kind of ask, what's the query complexity of LAZYSP? And I'll define query complexity shortly, but basically it's how many edges does LAZYSP evaluate? And the complementary question is it the best algorithm out there? So can we do better than that? So this is kind of a summary of the result. The work is pretty technical and not that interesting. The interesting part is the story, how we combine everything together. So we analyzed this work on two different models of how these roadmaps are generated. One is a deterministic model where we have this roadmap and every edge is known in advance if it's collision-free or not. And here we actually show that in this deterministic model, there's always an instance in this family of algorithms in LAZYSP that is edge optimal, that computes the minimal number of edge evaluations, which is great. When we look at the somewhat more realistic model, which is a probabilistic model, we have here each edge is collision-free or not with some independent probability p. Things become a bit more interesting. So we have this construction where we show that no matter, that there's always a construction where any algorithm in LAZYSP is suboptimal. So that's kind of a sad result. On the other hand, we show that we can bound the query complexity of LAZYSP by roughly n over p. And we present a matching lower bound of omega of n over p for every algorithm that is guaranteed to be correct. So the summary here, the take-home message is that while it's not optimal, asymptotically the algorithm is optimal for this probabilistic model. Now, as I mentioned, the work is a bit technical, so I'm just going to give you a flavor of the results that we obtain, and I'm going to concentrate on this query complexity of LAZYSP. To do so, I'll have to introduce, obviously, the algorithm and a few assumptions, and then the actual proof is not that hard. So first of all, let's talk about lazy edge evaluations. The key idea is that we have two configurations, and we have a cost function that evaluates the cost of moving from one configuration to the other. And this is complex. This requires evaluating if the robot intersects obstacles, so it takes a lot of geometric testing. If we're talking about high-dimensional systems, a humanoid robot will also need to talk about stability constraints, making sure that the robot doesn't topple over. So this is a very expensive to compute edge. So this is the first assumption, that evaluating an edge is expensive. The second assumption, which is very common in motion planning, is that we can get an efficient to compute estimate, which is a lower bound on the true cost. And usually what you do is assume that the robot is not going to intersect the obstacle and just compute the length or the cost that the robot will have to traverse while taking this edge, assuming that the environment is collision-free. And the key idea here is to use the lazy estimates to guide the planner onto when and where to evaluate the expensive true cost of an edge. This is kind of the paradigm behind lazy computation, and there's been a lot of work that exploit this idea almost as early as the first works on roadmap-based planning, which appeared in 98, so 2 years after that, or 96, sorry, so 4 years after that, we already have the first lazy algorithms. Specifically, as I mentioned, I'm going to concentrate on LAZYSP, which was presented at ICAPS 2 years ago. So let's go over this algorithm. It's a pretty straightforward algorithm. We have a graph. We assume that someone gave us this roadmap, and we have a start and a goal node. And what we want to do is compute a path that connects the start and the node. So what we're going to do is we're going to search this graph only using the lazy estimate. So we're not performing any expensive collision detection. This is simply a graph search. These graphs are typically not that large. It's in strike contact to the previous talker, where we had millions of nodes. Here we have typically thousands, tens of thousands. The problem is edge evaluation. So we're going to search this graph, and we're going to find a path. Now we need to ask, is this path collision-free or not? So we're going to now use the expensive to evaluate function, and we're going to validate edges along this path. If the path is collision-free, it's great, we can report it. If not, then we need to update our graph. We need to correct it. We need to remove edges that are found to be in collision. And the key question here is, how do we check edges along this path? And this is done using what's called an edge selector. An edge selector is a function that gets a path and tells us what is the next edge to evaluate. And I'm going to give some examples of the edge selectors, and this is what turns it from an algorithm to a family of algorithms, which is instantiated by the specific edge selector. So let's visualize this idea. Again, we have a roadmap here. The edges in dashed blue are lazily evaluated. So notice that some of them, say this one, intersects an obstacle. Let's run this algorithm. We're going to compute a shortest path tree. So here we computed it. And we're going to compute the best path. So we have here the light blue path. In this case, we're going to start evaluating edges from start to goal. So evaluate edges, they're collision-free until we hit one edge that is in collision. Now we need to update our graph. So all the subtree emanating from this edge is, we don't know if it's the true shortest path, so we need to correct it. We call this a rewiring operation. So we do this local correction, and we compute the next best path. In this case, we go through a whole different homotopy class, and we again start evaluating edges in this path. In this case, all edges are collision-free, and we find the path to the goal. And it's pretty straightforward to see that the algorithm is correct and optimal, because we have a lower bound on the true cost. So I talked about an edge selector. What is an edge selector? Let's formally define this. An edge selector is basically a mapping. We get a path, and we have the set of edges that we already are known to be collision-free. And we have the edges that are known to be in collision. And we need to return the next edge that we want to evaluate along this path. So I have some pretty straightforward examples of these edge selectors. Forward edge selector, basically this is what I ran in my cartoon earlier, where we evaluate edges, the first unqueried edges along the path. We have the analogous backwards edge selector, which goes from the target towards the source. And we can have, say, a bisection edge selector, which queries the first unqueried edge in this path, which is farthest away from queried edges. And in the original paper, they showed more sophisticated algorithms, edge selectors, that try to reason about the structure of this graph that exhibit better properties. For the sake of this talk, these are kind of simple and very intuitive examples of edge selectors. What I'm going to use in this talk is a specific property of edge selector, which is called connective. A connective edge selector is one that connects two connected components of the graph induced by the set of vertices and the set of queried edges that are collision-free. Wow, I'm running very late. So a forward edge selector is connective, a bisection edge selector is not connective. And this is kind of the main result that I'm going to show you, the technical one. So what's the cost of LAZYSP with respect to number of edge evaluations? If the edge selector is connective, then, and each edge is selected with probability p, then for every bound that you give me, delta, we can show that with high probability, 1 minus delta, we'll get roughly n over p edge evaluations. And the intuition here is pretty straightforward. The first question that we need to ask is, how often do we get a successful edge evaluation? Can someone throw this online? It's an easy question. Everything here is easy. Okay, roughly every 1 over p. If each edge is collision-free with probability p, roughly every 1 over p edge evaluations, one of them is going to be collision-free. Second question, how many successful edge evaluations can there be in total? Again, someone? I didn't assume I'll get answers. But again, this is not hard. If the edge selector is connective, we start with 0 connected components. At most, after n minus 1 iterations, we have a connected graph, and then we found a path between the start and the goal. So these are the two main, pretty straightforward ingredients that we're going to use in the proof. So let's set m to be roughly n over p, and we want to bound the probability that the following event will occur, that the cost of LAZYSP is going to be large. It's going to be larger than this m of roughly m over p. And the way to do it is using m-independent Bernoulli variables, where the ith variable, of course, is 1 if the ith edge that was queried is collision-free, and 0 if it's not. And this is kind of, don't let this slide be too scary. Basically, the probability that our event will happen is the probability, using conditional probability, this is probably second lesson in probability, that LAZYSP queries a small number of edges, less than edges, times the probability that all these edges are free, plus that LAZYSP queried n free, more than n free edges, times the probability that this will happen. Now using the intuition that I mentioned in the previous slide, the probability, this guy, the probability that we're going to have a very small number of edges that are collision-free, we can bound this using the Chernoff bound. This is basically the first question that I asked. And the second one, we know that because f is connective, we're not going to have the case where we're going to query a lot or more than n collision-free edges. And if you figure out the math, it's not too hard, then you can show that the event happens with a very low probability. So this is kind of a sketch of the proof and a flavor of the results that we get here. What's more interesting, okay, so this is kind of the question that we set out to ask. So what's the query complexity of LAZYSP? We give bounds. Is it the best possible under different models? Under a deterministic model, it is the best that we can hope for. Under the probabilistic model, it's asymptotically the best that we can hope for. So I'm only talking about good things about LAZYSP. Let's take a step back and talk about a bit not as good things. So every time LAZYSP assumes that an edge is collision-free, then, and it's not, we have this whole subtree that we need to rewire. And we can do this efficiently using LPA star, but still LAZYSP spends a lot of time on graph operations and not on edge evaluations. And the question is, do we really care about edge evaluations? So this talk basically says that LAZYSP is the best that you can hope for in terms of edge evaluations. But we don't care about edge evaluations. What we want is the running time of our algorithm to be small. And what we actually want to do is balance edge evaluations with graph operations. And for those of you who attended Aditya's talk yesterday, we actually showed an algorithm that allows to balance between these two properties. And this kind of closes the question on optimality and what do we care about. And that concludes my talk. Thank you very much.
Yeah, I guess I have two questions. The first one is about the independence assumption, because you could have 2 points that were very close together and an obstacle that blocks both of them. And so does that mess up the theory very much?
Yeah. I mean, the theory kind of assumes that this is independent, and we know this is one of the shortcomings of this analysis. It's pretty hard to do this analysis for when edges have correlation, and that is a very valid point.
So the second point is about you're counting the number of edge evaluations. Are they really all the same cost?
So in typical robotic applications, the edge evaluations, the cost of evaluating an edge is proportional to its length. If you want to be realistic, in order for this analysis to be more realistic, you need to subdivide edges into kind of uniform length, and then the analysis would be relevant. So you need to do this pre-processing step.
Thanks.
Another quick question, maybe? I've got a quick one. So there's been a recent bunch of work on
You have your own microphone on the floor.
There has been a recent bunch of work on combining roadmap-based motion planning with temporal reasoning. So when you have 10 windows, deadlines, can you comment on how this analysis relates to scenarios when you have deadlines?
That is a good question, and I'll need to think about it. Definitely not on the top off the top of my head.
Fine. Anyway, let's thank the speaker.